Hey sports fans, welcome back to All the Math. That's all the math you need for computer science. It has been a long haul climbing all the way up here to episode 8, but hopefully the vista that we see today is worth it as a payoff. We're going to be looking at some of the most beautiful math I have ever seen. Now let me tell you, I've seen a lot of beautiful math in my life, right? I've been around the block. There's a lot of things I've seen that'll take your breath away. But if I had to pick just one thing in the entire mathematical universe to sort of say, this is the thing that made my jaw drop the most, it might very well be the eigenvalue, eigenvector stuff that we're talking about today, okay? It'll make your eyes water. Eigenvectors, eigenvalues, which I've hinted about in previous episodes, have to do with seeing the matrix laid bare, seeing the deep heart of the matrix and what its activity is and what its operation is on vectors that it's multiplied by. And there's a lot of things in linear algebra that seem just like a mess of numbers scattered around until you grasp what this episode is about. And I hope you find it as cool and breathtaking as I do. I'm going to come at this through a concept called the resonant frequency. Many of you have probably heard that term, the resonant frequency, okay, of a system. And you've experienced this if you've ever been on a playground swing, all right? So let me tell you about little Stevie when I was a kid. There were two different parks that my mom would take us to. Someday we'd go to one park, someday we'd go to another park. And they all had playground equipment and, you know, a seesaw and a wiggle walk and all that kind of stuff. But one of them had a swing that was not very high. Okay, if you looked up, the bar was not that far from the ground. And the other one, which I called the big swing park, is the one that had a higher bar, right? We usually went to the small swing park because it was closer. Now, when I would go on the small swing park, I would get on it and I would ask my mommy to push me, and she would, right? And we'd go back and forth. Whee! Whee! Yay! Wasn't that fun, right? So I'm sure you've all experienced this, right? And you go back, of course, at a certain rhythm, and that rhythm is called a frequency. A frequency just means the rate at which something is going back and forth, okay? It could be anything from a physical system to the electrical plug in your house. The current is going back and forth at a certain frequency, 60 times per second as it happens. But I would always get really excited when we go to the big park because I'm like, wow, I thought that one swing was fun. This one, we're going to be able to go higher and faster, man. So we would go to that new park. I'd be so excited to get on the swing. And I was always disappointed. I kind of forgot each time, and I was re-disappointed each time we went to the park because I discovered very quickly that, yes, you could go higher on that taller swing, but you could not go any faster. As a matter of fact, you had to go slower, somewhat annoyingly. Okay, so when we were on the big swing, it was like this. Whee! Whee! Okay, so if you've ever seen some of those humongous swings, like a King's Dominion, where for $20 a pop you can go, do those, give you a heart attack swings, it takes forever watching them, right, swinging all the way down there, okay? And I would complain at my mom and say, Mommy, push me faster, push me faster. She'd say, can't push you any faster. This is as fast as it goes. And I would try to pump my legs faster and faster to get it to go faster. Nope, couldn't pump it any faster because that's how fast it goes. And no matter what I tried to do, I could not go even as fast on that big swing as I did on the little swing. It wanted to go at a certain frequency, and you could not make it go any faster or any slower, interestingly. Okay? So that's an example of a resonant frequency. Now you ask why? Why is it that the swing was that way? Why is it that no matter how strong I am, man, I'm Dwayne "The Rock" Johnson or Arnold Schwarzenegger, I'm going to totally push, as hard as I can with my legs. Why can't I go? It's because the nature of the physical system weakens every frequency except for one. Okay, cancels out every frequency except the resonant frequency, dampens all the other ones. And the only frequency that's allowed to sort of take control on that thing happens to be the special frequency, and you can work it out based on the mass and the length of the thing and the acceleration due to gravity and all these things you'll learn in physics, exactly what that frequency is. But it resists moving at any frequency other than that. Okay? Another example of resonant frequency is any musical instrument other than percussion. Okay, so percussion sounds like it does because it's sort of a blur of frequencies when you hit a snare drum or something like that. But most musical instruments, which play, a melodic tone, if you look at them in terms of what they're doing to the air, they are vibrating the air at a very specific frequency, and that frequency gives rise to a certain note. And of course, if you move your hand up the frets or down the frets on a guitar, you're changing the length of the string, and you're changing what the resonant frequency is, okay? So I got a little demo here. This is a real champagne, or a wine glass that came from Stephen and Pretty Little Rachel Kay's wedding. With her permission, I'm doing this, right? Now I'm going to strike this here, and I want you to listen. Okay, so you heard the little thing. Ding, ding, ding. Always at that frequency. Now, why is it that frequency? Is it because I hit it just the right amount of force? And if I hit it harder, it would be a higher frequency, and if I hit it not as hard, it'd be a lower frequency. No, here's a slow hit. Here's a hard hit. Okay? Here's a hit where I kind of stroke the edge. Here's one where I just come right off it. Okay? Always exactly the same frequency. Here's another little prop. This is the champagne glass from Stephen and Pretty Little Rachel Kay's wedding. Right? So you hear that higher note. Always the same. Doesn't matter how fast I hit it. Okay? That's because those glasses, as well as every other musical instrument in the world, has a resonant frequency, and it resists and dampens all of their frequencies except for that one. Here's another famous example. You might have heard of this or seen this before. The Tacoma Narrows Bridge. Okay, so this is out in near Portland, I believe, and this is an old film, I think from the 1940s. But they built this suspension bridge, which is one of the biggest in the world at the time, and boy, when the winds kicked up, there were some shenanigans there. And I think if you look at this picture, you'll be like, wow, I'm really glad I didn't drive on that bridge that day. Here's another view here. And you can see, it's just absolutely going crazy. And there are all kinds of people just standing around looking at it, jaws dropped. And of course, the thing did actually plummet down into the Puget Sound and was destroyed. Luckily, no one was hurt. There was only one dog that was hurt, I believe. But again, why did that happen? Well, it's a complicated question. There's been a lot of civil engineers, like my wife, who have looked into the Tacoma Narrow Bridge catastrophe, and it doesn't all come down to the resonant frequency, but that was a big, big part of it, okay? The idea that when the winds hit it at just the certain rate, it ended up reinforcing that frequency, enhancing the amplitude, dampening out anything else, to the point where the whole bridge was doing rock and roll, man, even to the point where it ended up breaking. Okay? All right, now, what does all this have to do with linear algebra, you ask? I'm glad you asked. The answer is, you ready for this? Matrices have resonant frequencies too. Matrices have resonant frequencies, plural as it turns out. Every matrix is going to have more than one resonant frequency. But understanding how these resonant frequencies work is the key to understanding the action of a matrix. Okay? Now, this is what made all this come together for me, because a matrix, up until this point in my learning, and maybe this is true for you too, is really nothing more than a big collage of numbers that you can perform computations on, right? It was utterly unlike the one-dimensional functions that we learned about in grade school, right? So let's go back to grade school for a second and say we have a function. I'm going to say it is f of x equals, I'll just say 10x minus x squared plus 5, something like that, right? So you remember this from high school or something, right? And you'll remember that, you could draw a plot of this thing. And, this may look confusing at first, but as you kind of think through what is the action of f on the value x here, in other words, if you give it an input x, what is it going to transform that input into? And that's what a graph is, right? It shows for different values of x, what is the value of f of x? You'll see things like, well, we know it has to cross here at 5, because if you plug in 0 for x, you're just going to get 5, right? So that was always kind of a freebie there to say, well, it's going to do that. And then I can see, 10x, well, that's pretty steep, right? 10 units up for every unit across. So this is going to, go up pretty steeply here. But of course, this x squared term is ultimately going to take over, right? Because x squared is much more of a big deal as x gets big than anything times plain old x is. And so eventually there's a point where this thing is going to, kind of come back down, and it's going to come back down, and remember how parabolas look. And so that's the whole thing is going to look something like that, right? Now, what was great about this is that I could get my head around the whole function. I could say, all right, if you want to know the particular value of f of x for a particular value of x, yes, I'm going to need a calculator because I can't do these calculations in my head, but I can tell you just with one glance kind of sort of what this function does. As high as x wants to get, you're going to get a lower and lower value for f of x. And as low as x wants to get, you're going to get a lower and lower value for f of x. However, it's going to go up kind of sort of in the middle here. And in the middle, there's going to kind of be sort of a peak, at which point it's diminishing returns and it's going to go sort of down. Okay? So that kind of intuition made all kinds of sense to me as a junior mathematician. Okay? Now, contrast that with this. I'm just going to give you a 2x2 matrix here. All right? 3, 4, -5, 1, whatever. I just made up those numbers, right? Now we know that this matrix right here is in fact a function, because remember, we can multiply it by any other pair of things here, you know, x1, x2, and we will get out an answer. I'll call that y1 and y2. Okay, so if we multiply this by the vector 4, 9, we're going to get something out. If we multiply it by the vector 3, 3, we're going to get something out. If we multiply it by the vector 0, -5, we're going to get something out, etc., etc., right? So this thing is a function. In fact, it's called a linear operator, if you remember that. Linear operator. And that's because, did I spell that right? Operator, yeah. That's because it's 2x2. It's a square matrix, which means the inputs are the same dimensions as the outputs here, right? Now, suppose I asked you the same question about that matrix that I did about this function. If I said, you know, kind of what does this do to vectors? How does it transform them? You know, what vectors going in are going to come out with high values and what ones are going to come out with low values or whatever? This thing is a big mystery. I could play around with this thing forever and it just looks like a bunch of random garbage. And it's going to until we figure out eigenvectors here, okay? So I'm going to switch now. Okay, so square matrices are linear operators. They are functions that will take an input of a certain size and give back an output of the same size. Let's just take just kind of a random one here, right? Okay, so here's M for matrix, and I just threw some kind of random stuff in there. Let's take this for a spin and see what happens and how it transforms its inputs, all right? So suppose you take the vector 1, 2, just pick that out of a hat. So I'm going to multiply that by the matrix. So here, you know, the input to the function goes right here because we pre-multiply the matrix by it. And you can work out these numbers. You can say, you know, 1.5 times 1, -1 times 2, add them up, and you'll get -1/2. And if you do the bottom row times this with a dot product, you'll get 1.5, etc., etc., right? So all that shows is that 1, 2 as an input maps to -1/2, 1.5, okay? If you look at that on a graph, this is what it looks like. So 1, 2 is the blue arrow there. And the purpose of this matrix and what its action is on the vector 1, 2 is to transform it to the vector -1/2 and 1.5, okay? Doesn't look like there's anything useful there except it just randomly did something to it, right? Let's try the vector 2, 1. If we get the vector 2, 1 as an input to this thing and we crank it out, turns out we get the value 2, 0. So 2, 1 as an input gets mapped to 2, 0. And that looks like this. So this time it moved it in a clockwise direction instead of counterclockwise. Okay, yippee. Let's multiply it by -3, 5. If we do that, we get back -9.5, 6.5. And if you look at that on a graph, you're going to see it looks like this. -3, 5 got transformed to -9.5 and 6.5. Okay? Do you see a pattern here? No? Good. Because there is no pattern. This is all gobbledygook, right? In fact, here's my summary of what we've learned so far. Random stuff maps to other random stuff, okay? This is why matrices are perplexing before you learn about the eigenvector, eigenvalue stuff we're going to do, because it just looks like a haphazard treatment of any input, transforming it into some other nonsensical output. Okay, now here's the plot twist. What if we multiply it by -1, 1/2? Now that just looks like an ordinary vector like all the others, right? Nothing super exciting here. If we multiply it by -1, 1/2, we get back the vector -2, 1. So -1, 1/2 maps to -2, 1. Now I want you to just look at that for a second, this example, and see if you see anything unusual. You see anything different about this than we did for the other ones? If you look at it, you will realize, ooh, that red vector is exactly twice the blue vector. They're pointing in the same direction. So here I have the blue vector pointing at -1, 1/2. And then I have the red vector plotted just over it because they're in exactly the same line. It goes to -2, 1. Okay? So this vector exactly doubles in size when you multiply m by it. Okay? Now let's go a little further. Take that -2, 1, that red vector that was the output. Let's take that thing and feed it back into the matrix. Let's make the -2, 1 be a new input and multiply it by the matrix. Now we get -4, 2, which again doubled it. So if we have something at -1, 1/2 and multiply it by this matrix, boom, it doubles to -2, 1. Do that again, boom, doubles to -4, 2. Multiply -4, 2 by the matrix, boom, -8, 4. Boom! We have hit this matrix's resonant frequency. Every other vector, with one exception I'll explain in a minute, every other vector you multiply this thing just gets mapped to some other crazy stuff. But this one is special. This one, when you multiply the matrix by it, you get an exact copy of it, only scaled. In this particular case, scaled by 2, doubled. Okay? The special vector -1 and 1/2 has a special name because it maps to an exact multiple of itself, and it is called an eigenvector. By the way, eigen is a German prefix, which I've heard means something like one's own intrinsic deep personal property or something like that, right? So an eigenvector is something that really tells us that this matrix wants to move things to -1, 1/2. It wants to enhance those. It wants to double those. Just like the glass wanted to resonate at a certain frequency. Just like the Tacoma Bridge, unfortunately, wanted to resonate at a certain frequency. Just like the swing wanted to go back and forth at a particular frequency. So this particular vector, the matrix just loves. Okay? So that's our first vocabulary term. Here's the second one. It doubles in size every time. Okay? Not triples, not halves, but doubles. And therefore, its eigenvalue is 2. So every eigenvector has a corresponding eigenvalue. And we're going to say that this eigenvector's eigenvalue was 2. And that's because it doubled every time. All right? By the way, in math and in linear algebra, we are going to use this symbol, lambda, to represent eigenvalues. Okay, so don't be scared by the lambda. It's just a Greek letter. It's kind of like a y, except it got flipped on the x-axis or something like that, right? All that means is it's a number, a physical number. For us, it's always going to be a real number. And that represents an eigenvalue. Okay, all right, so the natural question to ask now is, are there any others? Wow, you found this cool one vector, Stephen, that when you multiplied by it, it kept doubling in size. Are there any others? So it turns out, yeah. How about the vector 4, 4? Plug that bad boy in as an input, and if you run the math, you'll see that you get out 2, 2. And of course, 2, 2 is pointing in exactly the same direction that 4, 4 is, right? It's pointing in a northeast direction. And if I put 2, 2 back in as an input to this thing, I'm going to get 1, 1. And if I put 1, 1 back into this thing, I'm going to get 1/2, 1/2, etc., etc. So each time I multiply this matrix by some vector in the 4, 4 direction, it gets cut in half every time. Okay? And that means that 4, 4 is also an eigenvector, a different one than our -1, 1/2 one was. And its eigenvalue is 1/2. Okay, so we found one eigenvector. And by the way, eigenvector, remember, anything in that direction is an eigenvector, right? It doesn't have to be 4, 4. It can be anything, as long as the two anythings are the same. Just like -1, 1/2, right? It can be any two numbers as long as it points in the -1, 1/2 direction, right? Okay, so then the next obvious question to ask is, are there any other vectors that have this special property? And this may surprise you. The answer is no. And you might say, well, gosh, Stephen, you gave up kind of quick. I mean, you found those other ones by trial and error. I mean, what's wrong with kind of looking for some more? Maybe there's some others that have this neat property. Nope. I can tell you right now, there aren't any. And here's why. An n by n matrix has n eigenvectors at most. Okay, most of them do in fact have n eigenvectors. There's a weird case where it'll have fewer than n eigenvectors. We'll talk about that in a couple of segments. But here's just fact to take to the bank. If you've got a 7 by 7 matrix, it can have 7 eigenvectors but no more. And if you have a 2 by 2 matrix, it can only have 2 eigenvectors, no more. Okay. Last vocabulary word for this segment: the dominant eigenvector. Okay, so a matrix has more than one eigenvector. This one had 2. The dominant eigenvector is simply the one with the largest eigenvalue. That's going to turn out to be crucially important. Okay, so in this example, from this little matrix that we just kind of made up, we found 2 eigenvectors. One of them was -1.5, and everything in that direction, so I can't overemphasize that, right? Any vector that points in that exact direction, whether or not its magnitude is exactly -1.5, is an eigenvector. And its eigenvalue is lambda equals 2. And then, of course, we found 4, the other one. That one's eigenvalue is actually less than 1, which means it doesn't get doubled each time. It gets halved each time, right? And so we would say that the dominant eigenvector is -1.5, okay? Now, once you learn what the dominant eigenvector of a matrix is, you can do some amazing stuff. And if you thought this episode was amazing, wait till you see the next segment.